Good morning, class. This is Luis Rivera, and I chose case study 5, being controller tuning versus fuel flow at fixed thrust, given it's one of the topics close to my heart in the options available. So let's first start with the problem definition. Um, Today we're looking at whether the fuel flow changes when we use the different controller tunings in the ANOVA dataset, particularly tuning A, B, C, and D, while keeping thrust constant. The ANOVA dataset is made up of 56 fuel flow measurements, accommodating 14 for each tuning. The main question that we need to ask ourselves is, do these tuning data sets actually produce different average fuel flows in order to make a database decision? Let's take a look at the data set here. 56 rows. Let's go into the hypotheses that we are going to be talking on. Uh, in order to answer the question previously related, right? The question being, do these tunings actually produce different average fuel flows? We need to have two basic hypotheses. I chose a null hypothesis, which basically details that all tunings use the same amount of fuel on average, and the alternative hypothesis that says at least one thing uses a different amount of fuel. This allows us to establish a baseline where they're all the same, or one is standing out. We have an outlier. Going into the decision criteria here, we use the standard rule, being that if the ANOVA p-value is below the 0.05, we say that tunings are different. If it's above that 0.05, we get to the conclusion that we don't have enough evidence of a difference. Sorry. If we do find differences, we're gonna use the follow-up test called the Tukey's HSD to figure out which specific tuning differs. Once processing the tunings, we have the outputs per category, A, B, and C, and D, as detailed here. We get that the p-value is extremely small, far below that 0.05 threshold, right? Detailed here, far below that 0.05 threshold, which means that the tunings do not have the same average fuel flow, and that there really is a difference that is worth looking into. That then gets us to the Tukey HSD result. The follow-up Tukey test shows that tuning C in our case study uses significantly more fuel than A, B, and D. A, B, and D show to be at least statistically similar to each other. So the big takeaway here is that tuning C is the outlier in the fuel usage. Now, with the data that we have, what can we conclude? What can we conclude is that tuning C, right? And let me show tuning C here. Tuning C's controller behavior likely drives fuel use higher, maybe through more aggressive corrections or less efficient fuel control. Sometimes we do this on purpose to adjust stability margins, adjust cooling effect in our gas bath, and various other reasons. So extra fuel is not necessarily a bad thing always. There are scenarios where we would like to have that extra fuel at our disposal. However, assuming we're looking into economy, into efficiency, then that the results shown here essentially detail that tuning C drives higher fuel use. In regards to why this makes us better engineers, the value of employing these strategies is super relevant, right? Learning this process is actually more important than the actual numbers. It teaches us to do data-driven decision making, which is a personal value that I always communicate. We learn to validate the system behavior with statistics, separate the real effects from the noise, from the subjectiveness that can sometimes poison decision making. and it allows us to communicate our findings clearly, right? Fact-based arguments always tend to be predominant in such conversations. So asking a question, testing it, interpreting results, that's something the engineers or actually anybody, as I have referenced in the past, any problem solver does constantly. And obviously making smarter decisions through data benefits us all. So thank you.